robotics in the classroom. And robotics, to make a robot, you actually need a number of things. You actually need to understand how the physical parts are put together, how to make things move. This includes combining pieces in the structure to give you a physical chassis, and then combining motors, pneumatics, servos, whatever you have to manipulate the physical world around you. This falls under mechanical engineering. Then you have electrical engineering. Most robots use some sort of circuitry, so understanding how those pieces fit together, what it takes to wire up sensors, and actually give enough power so that the robot can move around is all part of electrical engineering. And then you have the programming piece. Now, many robots don't need a programming piece. For example, BattleBots, correct me if I'm wrong, Casey, but you remote control those,
Yeah,
right?
mostly it's off-the-shelf hardware, so it's slowly creeping into it. So, but yeah, for the most part, it's off-the-shelf hardware, just radio control gear.
Yeah, but if you want to introduce autonomy into some of these, you actually need some programming to go into it.
And yeah, some of the newer power systems with the insurgence of brushless motors, there's a lot of tuning that's going on. So there's a little bit of programming involved to get startup sequences right, program like a deadband, current limits. So while it's not your traditional structured programming environment, you are adjusting parameters and writing small snippets of code to affect behaviors.
Nice. So some of that's algorithmic, you would say?
Yeah.
Yeah. So that features back into what would fall under computer science, understanding algorithms, programming, things that go into traditional programming but may not be an actual language. And that exposes children to the computer science side of things. And then you have computer engineering, which is a kind of a combination of computer science and electrical engineering. I was a computer engineering, that's what I got my undergrad degree in. And so you see both parts of the electrical engineering side and computer science side. You have to know both wiring as well as programming, but the crux of that actually is things like firmware and getting small microcontrollers to do your bidding, to send programs to them, and understanding that firmware may operate a little bit differently than what you would find as software on your computer. And you also get exposed to things like digital logic. I mean, things like AND gates and OR gates you may not see until later, but in robotics it could be things like combining sensor inputs. It's 58 degrees outside and you detect a bump. Okay, then move forward. So that's a brief exposure to your digital logic. So moving on here, we've got some statistics here that show the employment for the largest and smallest STEM occupations. These are actually the bars for the largest STEM occupations in May of 2015. There was a whole separate section on the smallest, but I'm just including the top 10 here. And as you can see, some of these robotics fall into. So the ones that I've highlighted in red here, there's software developers for both application side and systems, that would be your back-end type of stuff, and computer programmers. All of this falls under computer science or understanding how to interact with a computer. And mechanical engineering is also listed on here. So robotics introduces students to these, which are part of the top 10 largest STEM occupations a couple of years ago. So in addition to this, I've highlighted some ones that were predicted growth in which of these employment industries. Again, anything dealing with computers, most robotics, you have to do something with computers, as well as something in engineering. Now, what's not shown here is the indirect introduction to some of these topics. So even if you are not necessarily hands-on or you don't enjoy doing the hands-on part of building a robot, being able to work with a team, potentially manage them, communicate within your group about what's going on, present to your class. All of these are some of the soft skills that may not be covered directly by doing the robot itself, but are definitely part of working in a team to build a robot. For example, let's say you enjoy teaching other people about what your robot does, potentially being a project manager as part of your team, or pitching, sales, that kind of thing.
Yeah.
All factor in, and you get exposure to these STEM-related fields that aren't necessarily robotics or hard engineering. And then at the bottom, I've listed drafters and technicians. While that's showing a potential decline in the next 10 years, these are still necessary jobs, and getting hands-on with robots definitely introduces you to these types of occupations.
Yeah.
So back to why robotics, coming back to this whole question. You get exposed to a number of STEM fields, students do, and they have the opportunity to discover one of their passions potentially outside of the core curriculum. Now, Casey, I don't know about you. I did not have engineering anything when I was in high school.
Yeah,
Did you?
we had a little bit. It's actually, I'm wearing my robotics team shirt from high school.
But
So.
were you required to take that, or was this a
No,
elective?
it was an elective. So a lot of
Lucky you.
schools, I think it was still an elective credit, or ours was mostly after school. But yeah, I know a lot of schools are gearing up with robotics teams and robotics after school activities. So, but yeah, no, it was a great multidisciplinary study. So, building robots, it requires math, science, the team building side of it, working with customers. There's just so much you have to do to make a working system. You got to work with so many groups of people. So, I mean, I think it's a really good way to like round out students and really give like critical thinking skills. So
Yeah,
I think
especially if it's not something covered in your core curriculum.
Right,
Either
right.
you can build it into a science class or have it as some sort of after-school program.
Yeah, absolutely. Yeah, it's a great way to kind of bring. So while in class, you're going through the fundamentals. A robotics program is a great way to kind of bring everything together. So your math and your science, documentation. Oh my goodness, understanding how to write and communicate with other teams is such an important thing. So it's a really great vehicle to show people how to use a lot of the skills that they've learned and bring it all together. Kind of give that meaning to why am I learning this?
Yeah.
So.
Something else is that teamwork. It opens up pathways, like Casey mentioned, communications between the different groups. More often than not, you're not going to have one student making one robot. That's actually pretty difficult. In almost every robotics thing I've ever seen in a school, it's teamwork, groups of 2 through 10.
Yeah. I've tried. It's miserable.
What, doing it on your own?
Oh yeah, no, it doesn't work. There's just too much. There's just too much to know. So what's great about it is it also gives some students the ability to like specialize. So you can it gives kids that freedom to kind of start playing with a bunch of ideas and where they like to be, they can gravitate towards that. So whether it's the hard skills or the soft skills, there's just boundless opportunity.
Yeah, it exposes them to all of that.
Yeah.
Not just the 4 engineering disciplines I listed earlier.
Yeah.
With the communication, kids understand what it means to be part of this whole. You're working on one piece, like Casey said, and integrating it in the end to create a working system, which is usually a lot of fun. And that's the other thing, is this is fun.
Yeah.
If I had a program like this in high school, I would have been all over this. Kids get to explore their creativity. They get to, both in the sense of coming up with new ways to solve a problem. If you give them, whether it's a fighting robot or a robot that needs to go through an obstacle course, coming up with ways to solve those, you begin to explore the creative side. And I find that the kids often have a sense of ownership and pride about their robot.
Absolutely, yeah.
They go nuts with decorating these things.
Yeah. Especially, if they get to go out and show it to other people, that element right there, like that's where the pride is. It's like I want to do well. So they really kind of pour their heart and soul into it, and it's something that they create, they made. It's their crazy idea. So I think it's great.
I did first robotics. I was a mentor for 1 year.
Oh my goodness.
And, you understand. You understand.
Yeah.
And
you've been in the trenches.
Oh yeah. So it was a great year, and the ownership these kids had over this robot. Then something I noticed is that even after the competition is done, there's still a part of the school year left, which means that the kids then take it and they go to pep rallies and they show off this robot, which seems silly when you think about it, but it really creates a sense of pride for them, and the rest of the students really enjoy seeing it. The rest of the student body's amazed at what these kids can do. And then when I was at Maker Faire this past weekend, there was a whole set of tents where the local students show up with their first robots, their first robotics robot that they had made for 6 to 8 weeks, something like that.
The turnaround is incredibly short.
6 weeks is a very short amount of time. I've got some stuff on First Robotics later, but these kids love it. They show up to Maker Faire and they show it off. It's a community outreach, and it gives them that sense of group pride and accomplishment.
Yeah.
So, before we move on to Casey's section here, just to let you know, if you have questions for us, write them down in the chat section, and we will get notified and attempt to answer them as best as possible. So, Casey, you want to talk to us about the design cycle?
Yeah.
Something else you can learn.
So the big thing, in these competitions, with first and with best, and with the combat robots and even AVC, Some cool things is, having a challenge that's somewhat similar from year to year gives you the ability to kind of give kids some exposure to the design cycle. So if you have students, multiple years, if it's an extracurricular activity, typically you'll have them, between two to 3 years. So, and there's some really awesome things that you can do. So, I'm going to draw from a lot of personal experiences, and the basic here is, how did we get here? So, I was on a team for ABC's BattleBots, and so our lovely green machine here, and people ask me, oh, well, how'd you get started? And they all expect, some grand answer of, well, I started at a whiteboard and I designed this. It actually started out me riding a robot in a parking lot and not knowing what I was doing. That was not one of my smarter years. But the thing is that everybody starts small. So, the idea the first year we built robots was, can we just get this thing to drive? And every time you build one of these iterations, I'll go through, iterate. Every one of these designs has an advancement on the next. In this case, the one in the center was our first design, and then all the way to the left side was kind of one of our later designs. And you learn so much every time you compete, every time you build something. So how do you do this? So the first thing I always there's a pattern. You got to learn the design pattern. So you design, test, analyze, and redesign. So design it. Let the kids go nuts on the whiteboard. Try to guide them a little bit, but if they got some wacky idea that they are set on it, let them do it. Let them experience that. I find that students learning from a failure is far more beneficial than just telling them how to do it the right way the first time. It just you don't understand how much you learn from a failed test or a failed system. So that's where you test it. Set up your parameters. Whether it's a combat robot, whether it's a line following robot, set up a test. What's your criteria for passing, failing? And then analyze that. Analyze that test. What went right? What went wrong? If you had a failure, where did it fail? Where did things break? Where do I need to add supports? Where do I need to fix my code? There's just so many things that you can do for that. And then the idea is that if you can redesign and incorporate those changes, that's what I think gets kids really excited. Is once you get through that redesign process and they implement those changes and they see the problem either solved or get better, then it drives it home what the analysis can do. So then
this is true for real engineering too.
Absolutely. Even in I build spacecraft for a living, and we always build one unit first, and we run it through a bunch of testing, and we figure out all the points where it fails or it's not quite right, and then you correct it or you make it better, and then that's when you do your next article. And sometimes you can go through that cycle. You can go through it once, twice. Sometimes, I've seen programs that have done 6-7 iterations, you're doing continuous improvement, and it's really cool to see a design evolve over time, and you kind of develop a style of how things are built, and that's pretty neat. So design by analysis or test. So when I was a high school kid, I didn't really have access to a lot of stress analysis tools. So my design was through testing. So I built something, I tested it, and I saw it's a very empirical way of doing things, and it worked for what I was doing. One of the biggest things that once I got to college, analysis was key. So the idea is that you try to analyze your system to death. You've seen paralysis by analysis.
They give you a problem and they're like,
yeah,
"Well, just solve it," and that's
exactly
most of college.
Frictionless spherical elephants. So, but in the real world, it just you can get 95% of the way there with analysis, but you just don't know until you run the test. So so then the next thing is that with these iterations, Another opportunity you can teach students is risk reduction. So let's say we have an unknown in our design. We don't know if something's going to fail. So what do? How do we reduce that risk? And there's plenty of opportunities, whether you can design secondary safety systems, You can design like grace. I call it failing gracefully, and so you can bring that in there. And then there's risk mitigation. So let's say we have a problem. A motor starts binding up, or something, and we find out that okay, well we've actually confirmed that the course that we're running in is getting dirty. So how can we mitigate that risk? Can we do it through, can we change the design? Can we put covers on the system? Can we turn it into a maintenance procedure before each competition? You gotta clean your gears or re-lubricate them. And so these are the things that you can get. This is where you get students thinking about not just building the design, but operating it. It's great to have a robot work for, 30 seconds on the table.
You mean like these guys?
These little guys.
Yeah, these things were working as of like 3 days ago. We booted them up right before this webinar, and they were all over the place.
Yeah, there's just
one of the motors isn't quite working. Yeah.
Yeah.
And it's one of those you learn, right?
Yeah.
You have to dig into it and figure out how to make it work. Because if I'm going to go compete with these, it had better work when I put it in that arena.
Yeah. So the idea is, getting students used to the competitions get students used to maintaining their robots, and they learn. I designed this crazy mechanism, but to fix it, I have to get a screwdriver inside of a hole and up through a tube, impossible to work on. So, so then, these risk mitigation techniques are, hey, do I tool access? That's something that's rarely taught to engineers. Looking at you, aerospace. And then, sometimes, analysis is great. Like, let's analyze the problem on the whiteboard, but how fast is it to test something? Software is so forgiving to test things in real time. Students can kind of just throw things at the board and see what sticks and just go for it. So, there's lots of opportunities to teach kids, critical thinking, not just in solving the problem, but how to solve the problem. So. And yeah, so continuing on that, so we're iterating. So we got students iterating, and so what do we want to do? We want to build continuing knowledge with teams. This is me rocking the socks off of our Director of Space grant. This was me building a robot back in years ago.
I love the NASA look here with the short sleeve, white button down, and black tie.
I think I was like a freshman or sophomore. I was just like so in love with the space program in the the 60 cents, but the thing was is that over the years, we started to you kind of start building up a knowledge base. You start understanding the pros and cons of different methods of solving of doing things. Like, are brushless motors great? Are brush motors? Is it lithium polymer? Is it lead acid? And so, over the years, we've collected data, whether it be hard data, whether it be anecdotal. Just having that knowledge, and what you can do is when you have senior members of your teams, you get your juniors and seniors, and you have your freshmen, sophomores, or you have your 8th graders and then your 6th graders. I almost say like weaponize them. Turn these kids into educators. Let them help you teach your classes, because once they know something, they want to tell somebody that they know something. So, whether it be outreach events, that's the first robotics. These kids, they work their butts off for 6 weeks, and they've learned so much, they've done so much, and now they want to tell the world about it. So, bringing that into, from juniors and seniors, having a JV team or something, and having, the juniors and seniors help the underclassmen, it gives an opportunity for making leaders out of the teams. So, some people, they want to work on the problem. That's what they want to do. But there are others that really kind of want to lead programs, and there's plenty of opportunity to let them teach the up and coming groups. So it's a great way of just kind of facilitating this kind of learning environment. And because robotics is such a wide open field, and there's just so many ways to attack it. There's limitless possibilities. So there's no bounds to how much you can grow the programs. So
sweet. All right, my favorite part here, a history lesson time. So let's talk about what it takes to actually how did robots get into the classroom, at least how we see them today. And Lego Mindstorms is one of the more popular kits that you can get, I would say. I did them.
I had one. I remember when it first came out. It was the yellow. It was the RCX.
Yep, the RCX.
Yellow brick.
Yep.
So tiny story. So my parents got me one of these things for Christmas, and they told me I just begged and begged and begged, and I saw this present under the tree, and I
Did you shake it?
I knew the box size. I knew the dimensions of this thing.
Of course you did.
I had studied it. And something I didn't tell my parents this until probably 10 years later. But what I had done is I went with a razor blade and I peeled it open. No, even far worse. I peeled it open. I opened the box and I emptied everything out and I stuffed it under my bed. So I love this set to death. And so by the time Christmas came around, I stuffed it all back in, opened it up, and I was like, I'm surprised. And then
I've built this robot already.
Yeah, exactly. Somehow this thing already works. It's already programmed.
Oh, it came built. How did that happen?
Yeah. So, but yeah, no, the Lego RCX and the new NXT series.
The NXT, they're on EV3 now, which is basically a full-blown Linux computer.
Yeah, amazing.
Yeah. So how did that come to be? Is it actually a fascinating story? Why did we get programmable Lego bricks?
Tell me.
What? No.
Tell me.
So, does anybody recognize this? Too bad I can't see a show of hands. The role of the teacher is to create the conditions for invention rather than provide ready-made knowledge. And if you know it, pat yourself on the back. This is pretty good. This gentleman's name was Seymour Papert. He was born in 1928, and he was South African and moved to America, and he became a teacher and researcher at MIT. He eventually developed this theory of learning called constructionism, which is based on Jean Piaget's theory of constructivism. And the idea is that it's student-centered discovery. It's no longer just teachers blabbing pieces of information and then testing the students to regurgitate that information. It's really about getting the students involved, and a lot of this is based around project-based learning or problem-based learning, where you present some type of problem for students to solve, and it's on them to figure out the answer. In this case, teachers are facilitators and coaches, kind of guiding the learning and the process rather than being lecturers. And Papert said that it's most effective when students make objects in the physical world. They have an idea, some abstract concept, and then when they bring that down and actually make a physical object of that representation, that's where the real learning occurs, according to this theory of constructionism. If you're curious, Papert's book, Mindstorms, Children, Computers, and Powerful Ideas, came out in 1980. You can still get it on Amazon, and it's a pretty good read. So recommend checking that out if you want to see what Papert was talking about in all of this. But let's talk about the logo language, because Papert had a hand in this as well. So 1967, Wally Fierzig, Cynthia Solomon, and Seymour Papert developed this language called Logo. And if you grew up in the 80s, Casey, do you recognize this over here? There's a little turtle.
Might be a little.
Really?
Little
I thought we were about
me.
the same age.
But I didn't grow up with computers.
Okay. Well, see, I didn't have the robotics thing in high school, but in elementary school we had Apple IICs. We had a computer lab in elementary school. This was late 80s.
I played a lot of Math Rabbit.
I think I had the space one that you had to solve the things with. Yeah, I remember the name of that one. But well, one of the things we had in elementary school was this thing called Logo, and it was a little cursor. It looked like a little triangle in the middle of the screen, and with a little command prompt, and you would say, draw a circle, and it would actually draw a circle on the screen, draw a square, draw a line, and you started to develop concepts of math, and what math meant in geometry sense. Like, what does a point between here and look like? Oh, that's a line. And I can draw a circle and start understanding what a radius means, all without really being presented the math concepts. It was a programming language, and it was developed specifically for education. The little triangle you see in the middle there was a cursor known as a turtle. And Papert went on to work with real robots that he also called turtles. And these, you attached a pen to it and it would draw shapes much like the virtual turtle would in the programming language, our little interpreted language here. And these became the physical manifestation of these abstract concepts. So in the Logo language, where I could say, hey, draw a circle, and the little turtle would on screen draw a circle, now the robot was doing it in real life. And that's just the next step for being able to understand what these abstract concepts, especially ones around mathematics, involved. And it also created an environment of play. This was fun. I got to tell a robot to do a thing, and it did it.
That sounds awesome.
Right? Right? We never had the physical turtles, but we got the little Logo program in our computer lab, our Apple IIc computer labs.
Man.
Right. It was a good time. So we have Lego. Enter Lego, the big company that we all know and love and probably grew up with the little building bricks. In 1984, Kjeld Kirk Christiansen, the then CEO of Lego, watched an interview with Seymour Papert and discovered that Lego, the idea of Lego, which then had just created its education group, fit within the philosophy of constructionism. And Papert was the leading person behind constructionism at the time. So he flew down and met with Papert, and Papert met with, Christiansen met with Papert at MIT, and they worked on ways to combine Lego and Logo to create some sort of programmable brick, which we saw a few years later. And this came out of MIT Media Lab. However, you notice it's 87. It wasn't until 1998 that we got our first programmable Lego kit, which was known as Mindstorms, based on Papert's book.
Yeah.
So yeah, it's an homage to Papert's book is where that name comes from. So now you know,
Awesome.
Mindstorms. Yep.
I learned something.
Yeah, there you go. I taught Casey something. Hooray! So that's, now you understand how how Lego interacted with Logo, working with Papert's idea of constructionism to be the Lego kit, the NXT, and how we got like the EV3 and why that continues to be so popular in schools nowadays.
Yeah.
So
Awesome.
engagement.
Well, engagement. So how do you get kids interested? So like, you know, I went to engineering. You know, I went to physics school, kind of an engineering physics campus, and so, you know, by the time I got into it, you know, I was already excited about everything. But in high school, I was not quite as excited as I probably should have been. So how do we get to this crazy kid on the left? So that was my first BattleBots tournament. I was excited, very excited, too excited.
You look excited.
Way too excited. And so, what was so appealing about it? So BattleBots is what got me into all of this. Oh, thanks.
You got a close up right on your
Great.
face there.
So
it's Tiny Casey.
yeah,
Tiny
yeah.
Casey.
So youthful. Don't. Yeah. I don't even know. Okay. So, anyways, so the reason I was so enamored with BattleBots is, one, it was on TV. Two, it was robots destroying each other. And three, it had a bunch of sparks and fire. And, you know, I was just like, this is like dirt bike racing, but they're running into each other. I don't understand it, but it looked awesome, and I wanted to be a part of it. So you know, that makes the problem, you know, relatable to me. You know, I was, you know, 14, 13 years old, and just like wanting to see explosions. So BattleBots had that hook for me. And so that's how I got started, and then afterwards I started into the like the robotics challenges. Best Robotics was a big one that I was a part of. Never got the opportunity to do first in high school, but I was a mentor for 2 years.
Oh,
And-
you did it too.
Oh man,
that's
we've done the time.
You went the distance.
So, yeah, so that is to all the teachers that do the 6 weeks and 8 weeks and year-round first, like, you were a godsend. So, so you know, what's the big thing is, like, make it relatable to the students. You know, as much as I love, you know, talking about, you know, perturbation theory, or like, you know, statistical solving methods of robotics, you know, like, that's a real dry subject if you don't have a use for it. So make it useful. Like, what do you want kids to do? You know, line following is something, you know, you can relate it to, you know, autonomous vehicles. You can make line followers with obstacle detection. You know, you're trying to stay in your lane, but what happens if the other car, you know, decides to drive into your lane? What do you do with it? How do you handle that situation? And so it's interesting is you can also, once again, you can show students how complex some of these problems are. And you can layer these things. You can start with line following, then you can do line following with obstacles, then you can do like synchronized line following.
Was it swimming?
Yeah, kind of. So, you know, and then there's so many ways that you can just continue to build upon a problem. So, you know, look for something that you see, you know, look for something you see in nature. So, you know, you have autonomous cars, you have, you know, Amazon robots doing logistics, you have, you know, things as simple as your washing machine, things as, you know, like, there's rockets now that can land and autonomously dock and, you know, do all these things. You know, maybe you don't have to start with a space program, but you know, you can make analogs to these things. You know, making a robot find a charging station, you know, that's it's kind of a good analog to, docking to spacecraft. So, bring in pop culture. I got to see Neil deGrasse Tyson talk once, and he said that that's like one of the most important things that the educators and scientists can know is understand pop culture, relate with students on a level that everybody understands. Bring in current events. Bring in there are celebrities out there that talk about science now. It's incredible. Like Bill Nye. Bill Nye was on, he was on like what, PBS and I forgot, like ABC or something.
Well, he has his show now.
Well, yeah, he has that now. But it's crazy how like, Bill Nye is now like mainstream pop culture. Like what?
Right.
Neil deGrasse Tyson has primetime television shows, and these are. These are things that inspire, they're great communicators. So
I got a question then.
Yeah.
So we know that you mentioned rockets being able to land. So you have SpaceX landing their spent stages on barges. We've got autonomous vehicles is huge right now. Every company's competing to make the first real autonomous vehicle. So that's something you could make either like a competition or some kind of just work together, a cooperative thing to make some type of, we're going to build a small scale autonomous vehicle.
Yeah.
Are there any other things in pop culture you think that are relatable that teachers can reach for and say the kids will probably know what this is?
Yeah.
Let's bring this in and make it into robotics.
Yeah.
So I think Minecraft, but where do you go with that?
Yeah. So I haven't played much with Minecraft, but I've actually seen simple things to understand mechanics and just radio control devices is like R2D2 builders.
True. Yeah, there you go. Star Wars is still big right now.
And so, robots with a personality. Can you program a personality into a robot? There's all kinds of the animated TV series based around robots. Just exposing these concepts and say, like, focusing students and saying, hey, let's look at like this little tiny subsection of it. And being able to kind of relate it to that, that makes, it gets kids engaged that way. So, and also, my next section is, make the problem interesting. Statistical solving methods, like without a real, understanding of what you're doing, it's a pretty dry subject. But, like I've said, with the autonomous vehicle challenge, getting kids out in a parking lot and chasing a robot around, like, they're either gonna tire themselves out or they're gonna figure out how to make the robot come back to them. So it's a win-win. You're mentally and physically draining them. So wear them out.
Parents will love you.
Yeah. So give challenges that interact with the world. Don't, like I say at the end, like, don't make it about code. Code is great. There's plenty of opportunities to learn software, but, robotics, I'll let it slide if the code's a little sloppy. You're more interested in, can the students solve the problem? I mean, there's a lot of critical thinking skills required to identify the problem, identify the steps needed to solve that problem, execute, and then analyze. That is the critical thinking cycle. So it's so huge to you can find something in pop culture, you can find something that's happening in the current news, and relate it to your lessons, and kids get excited about it. You can give them that sense that they're contributing something, and there's tons of projects out there with swarm robotics, swarm behavior, simple like beam robots, that like photovores and photopoppers. There's lots of big projects out there that are trying to study like insect behaviors, and there's just all kinds of things that you can get students, actually, helping real science. So, and it's just doing, really little small bits, and break down the problem, and show how, show the elegance of the solutions, or show the complexity of the problems, and kind of be like, it's okay to, as it, every teacher knows at some point, it's okay to be like, I don't know this, I don't know the problem or the solution. So, but here's the problem. Let's see what you guys can do. Don't make it, rote memorization. That's the best part about robotics, is it's, there's skills that you need to know, but a lot of it is just kind of thinking about the problem. So, and, so I go in, make it drive. Make the robot do something, like drive in a line. See that kid right there? I bet that kid slept great. And his parents were so proud of us at AVC to wear him out because he was chasing robots around. AVC is a great opportunity to make robots interact with the real world in a competition setting, and it's a known problem that's kind of stable year after year, so you can increment on that. So make it art. With STEM education, they're trying to get more arts into it, so you get the STEAM folks. This is a program that I did. It was like a workshop, and you get kids of all types. So you get this lovely star robot. You get this, like, I call it the modern art piece. I think I challenged this student to put as many googly eyes as possible on there.
It looks like he used them all.
Yeah. There's a ton of them, and then of course at the bottom. So we had like a basic robot kit that was a photovore, so it looked for light. So we don't have any programming. We don't have any soldering. It was just kind of this built like hodgepodge of motors and wires that they just kind of hot glued together into something. And so it gave it. This is like a K through 12 activity. And it gave students just an opportunity to play with a robot and kind of like discover its behaviors. So, we put a bunch of spotlights up and we put a bunch of obstacles, and the kids, it was more of an art project than anything. So the kids got to build their robot, and yeah, you have all these designs. And my favorite one is the one at the bottom. We clearly have a civil engineer on our hands.
Yeah, that's a barge.
I'm pretty sure that is a bridge.
That's a bridge.
I think so.
Sticks?
I remember asking. I was like, so why'd you build this? And he just said, I wanted it to be strong. And I was like,
you're surprised you're a civil.
You win. So that was a It's interesting just to see what kids come up with. We didn't tell them, so I really intentionally didn't provide an example. And it was really kind of fun to see the kids like struggle with it a little bit, because I know in kind of that K through 12 it's a lot of mimicry. You see what the teacher does and then you replicate it. And so watching kids kind of build something completely from scratch was really fun. So
without any sort of like seeding.
Yeah. We tried not to. I think we pulled out a robot like halfway through the build, and so the kids that were getting stuck could kind of see something, and
this is where the creativity side of it really comes out.
Exactly.
You have to accomplish your mission, but how you get there is really up to you.
It's just put glue motors to sticks. That's just great. So, and then finally, make it fight. These are robots that I built over the years, and it's a great way to get kids engaged.
This is the TV show on the left here, right?
Yeah. So that's Poison Arrow was our BattleBot, and it's getting slowly wrecked by Bombshell. It's good times. And then this one is it was actually our first iteration of the drum bot on the right side. And so what's funny is that these are 120-pound versions. So that's a 120-pound version of Poison Arrow, and it's a 120-pound version of Tombstone. The guy that's the team that won the season we were in. So it's been great. So I love the team aspect of kind of the team events. You build like these lifelong bonds. All the students that I was co-team members with in high school, a lot of them I'm still friends with. There's still kind of a professional network that you build from that, and you make these great friends along the way. Competition, healthy competition, promotes. You're trying to kind of one up each other, but at the same time you want to help each other out and solve really cool problems. So whatever you can do to get the kids interested. Sometimes it's not going to be hard science, or sometimes it is going to be hard science. Whatever gets them going, use that as leverage to get them to think about other problems. The idea is you give them a little bit of sugar for the medicine. So give them a little bit of something to look forward to, and they'll work, they'll put in the hours. I mean, I can't tell you how many hours I spent doing things I absolutely hated, like tapping holes in metal. I just I can't stand it. But that's just part of the problem, So yeah, go for it.
You get that final robot. It feels
it's such
something you worked so hard on.
Yeah, to see everything come together with all your teammates. It's really it's really awesome to see a robot do its thing. You know, whether it's a combat robot just driving. I've done some autonomous vehicle work, and seeing it just like out in the field, just doing something simple as taking a right turn, like AVC, like watching a robot take the right turn. It's like it knew how to do that, and you know I didn't tell it to do that. And
you get points just for making that first turn in AVC.
Exactly, and
it's hard. It's not actually
it's
that simple.
Yeah. So you know, and being able to do things like that, it lights the fire. So you know, and that's what gets you hooked is seeing what you've done do something, and just kind of like standing back in awe of, you know, what you've accomplished. So you know, whatever you can do to get these kids hooked, you know, do it. So
sweet. So that's pretty much the end of our explanations to
Yeah.
why robots are good for the classroom. So if you're curious about some places to go to get some inspiration about what you can do, I've got some resources here for you, so I'll bring those up. Ideas for challenges, and this list can go on for days and days and days. What can you do in the classroom to get people interested? Where can you start? And usually it's some kind of competition, but it doesn't necessarily have to be.
Right.
It could be all the students working together to solve some communal problem, but a lot of the easy to get started with ones are your basic competition. For example, we've got combat bots. Casey, you just told us about your combat bots, and I've got a couple of bots here. You want to hand me a controller?
yeah, I'll give you this one.
All right, let's move your glass out of the way. I get the
All right.
terrible one.
Yeah.
So these are, just to give you a story, these are plastic ants. The idea is they are 1-pound robots that you make. So there's an Arduino in here. It has a receiver that receives signals from this and translate it to motor drive. And these are supposed to have some kind of active weapon to make it a little more interesting in the arena. They're supposed to smash into each other. But the simplest design you can make is just a basic wedge. Wedges actually do pretty well even against active weapons.
Wedges are like the best thing you can build. The lamest thing you can build.
It really is. It's a passive weapon. You push each other around, and they're usually strong enough they have no internal failures. There's no spinning weapon on them.
It's a very simple design. It's a great starting point. And it's the least destructive as far as educator classrooms. It is the least dangerous.
We can drive this on the table, and there's no going
to
be no flying bits at our faces. That we can actually do this.
I'm already winning.
Yeah, I just turned on my controller. And so all we're basically running a sumo match right now and trying to push each other off. Now, I'm actually competing against the real battle bots.
Oh, I was never a good driver.
You were the builder.
I was the guy who made things work. I fixed it. Oh no, I don't even know where I'm going. But yeah, so this is something that students can build in an afternoon. You know, of course they're going to want to drive it. You're going to always have that one student that's played just a little too much Halo, and they're always your driver. So, it builds other skills, hand-eye coordination. Oh, as a young nerd, that was hard. But, getting kids, driving something, building something and seeing it move, it's just, there's a sense of accomplishment with it. So, whether it's combat, whether it's sumo, all these competitions, come check out AVC. It's gonna be awesome.
So first of all, sumo. We basically had a mini sumo match here, and sumo is different from combat. Combat is all about. It's more like boxing. You try to destroy your opponent. Yeah. If they stop moving, you win. If you what is it, like number of hits, you can get scored on aggressiveness and across a number of fields. It's very much like boxing.
I call it hardware penetration testing. So those of you that are in information technology. So the idea with combat is it's like, it's kind of this hardware penetration like Formula One of robotics. So you're really trying to make a system run at like maximum performance. You got 3 minutes in a ring, and you're just trying to go 110% the whole time. So
you spec your batteries to last that long.
Yeah, that long, and just go for it. So it's an interesting challenge in that sense. Sumo is
elegant?
Yeah, elegant. It's like the fencing. You have boxing.
What is a lightsaber? A weapon for a more elegant?
Exactly.
How did that line go?
Yeah. So BattleBot's a little bit more barbaric. Sumo. There's a lot more strategy involved with sumo. So there's tons of videos. Just look up sumo robot.
The basic of it is you draw a circle and you have a couple of bots with equal weight, and you just attempt to push each other out of the ring.
Yeah.
So these wedges would probably work decently well. We were basically having a sumo match here. I'm not trying to destroy him. I'm just trying to outmaneuver Casey here. Have you seen Auto Sumo?
Yeah. Oh no, it's insane. Yeah. Look up Sumo Bot Japan, and they're amazing.
So what we were doing was remote control sumo, which did require some programming, but Auto Sumo is where you actually have autonomous sumo bots that attempt to identify their opponent and push them out of the ring using code. No human interaction, and these things are terrifying fast.
Oh yeah.
They're only about this big, but I recommend, if you haven't seen it, look up Auto Sumo, and it is a fantastic 3-minute watch.
It's nuts. Like these things, like they'll finish a match before your neurons can process what happened.
Yeah, they look like little bumblebees attacking each other, and suddenly one wins.
So and it's simple. It's 2 wheels and a wedge. Get students, and if you put a few obstacle sensors on there, what better way to promote kids to do better than the one next to you? So friendly competition. Get the students kind of get a little prize pool going, or
I don't think they can do that in schools.
Oh, that's right. Betting's illegal. But anyway, make some friendly competition of it. So you have a leaderboard or something. Who's king of the hill. So but there's all kinds of ways to sumo and combat.
Yeah, so those are 2 basic ones, 2 good ones to get started with, and those are more about design choices you make for hardware.
Yeah.
And the thing, if you're curious, before I forget, if you're curious, the design files for these are all open source. If you head to SparkFun's YouTube page, the last video I did under Adventures in Science, I show you how I put one of these together, and it lists all the design files, all the code. You just need to copy it, and you can make a bunch of these if you so desire. It does require a 3D printer. I don't know if you can see these, but these are 3D printed chassis, and then it's just a bunch of soldered wires and boards on the inside.
Yeah, pretty nifty.
Yeah, they're not bad. I got the design file from Jamie Lieben up in
oh, excellent.
Yeah.
Nice.
Not Fort Collins. Where is that?
Loveland.
Loveland, thank you. I
Yeah.
know my way around Colorado. I've lived here long enough. You'd think I would. So in addition to combat bots and sumo, there's a whole host of other things you can do. Line following, like Casey mentioned, is a good one, and you could take that to a competitive place and do speed races with it, or build in some type of obstacle course. I remember my junior year in college, we had to do a basic design class, and they built more of like project management into this. We had to do our designs, make design decisions, show the matrices, like present our designs to management at the time, which was our professor. And this was a basic line, and then we had to solve a couple of obstacles along the way. I think we had to like put balls through a hoop, we had to like pick something up, go over some rough terrain, and still maintain our traction on the course with the line. And then the fastest robot, won some kind of prize. No betting though. I know, I'm sorry. There's also autonomous vehicle. Casey mentioned AVC. Next weekend, SparkFun is running, there's a picture of it here, SparkFun is running our autonomous vehicle competition. This started, if I remember, this was a bet between our CEO and head of engineering. This was a Pete Doctor and Nate Seidel thing. They bet each other that they couldn't create a robot that would drive around the parking lot. And in our old building, the parking lot kind of encompassed the building. So really it was a race who could go around the building. Hands off the wheel. You put a remote control car on the ground, you push a button, and it had to drive around the building, and the first one to make it won. And that was how AVC got started. And how many years are we running this now? I don't know.
I want to say it's like 8 now?
7, 8? I should know this.
9
We're
years.
getting information.
From our production staff.
Yeah, our production staff. 9 years, so we're running AVC. This year it's taking place down in Denver as part of Denver Mini Maker Fair, or was it a full Maker Fair? It's a full Maker Fair.
It's a full Maker Fair.
Yeah, Denver
We've
Maker
gone full
Fair.
Maker Fair.
We've gone full Maker Fair. You never go full Maker Fair.
We're doing it.
We're doing it. We went full Maker Fair. And we're taking over a whole parking lot. There's several classes. One is the Speed Demons, and this is the robots as fast as they can with a few obstacles. There's one where people have to ride in it. Are they doing the Nerf gun thing? Is that legit?
I don't know.
I don't know if that was real. I
think that would be great.
Yeah, they're shooting Nerf guns at targets while they're riding in autonomous vehicles. And I know it's like one of those Disney rides.
One of those.
It's like Space. It's not Space.
Is it Space Mountain?
No, that was a roller coaster, I think.
Yeah.
Anyway, and then we're also running one called Logistics. I was part of this one, and so that's real. You have to go into an area, pick up something, drive autonomously to another area, and then stack and sort things, much like the Amazon robots do in their warehouses.
That's so hard.
It's not an easy one. We actually made it, you can remote control this, and you get points for doing certain tasks autonomously. So you could push a button, have it do a thing, or like have it do
Yeah.
certain tasks and say go do your autonomous thing, and that way you don't have to worry about doing everything autonomously because it's not an easy task.
No.
Other ones that I've seen are search and rescue. This is there's a burning building and we need to search for survivors, and that's a very common thing that people are developing robots for. It's a big thing, and I've seen it even when I was in school. There were competitions for this, and that is, can you build a robot that navigates inside of a crumbled building, and can you either extract someone or something out of the building, or take pictures and give your location so a rescue team can get in to help out. There's also rover exploration. NASA loves these. These are, let's go to some desert or something that approximates Mars or the moon, and you're going to take a 6-wheeled robot or however many wheels you have, and you're going to drive to a location and collect a sample and perform generic science on it, whatever it might be, or collect it and bring it back, whatever it is.
Mars Centennial Challenge is a big one up at WPI.
They do it every year?
Yep.
Yeah.
Yeah, you're trying to collect tennis balls from a field, but you don't know where the tennis balls are, and the tennis balls are about the same color as the field. So
do they have to do it autonomously?
Completely autonomous, and they have to
Wow.
deliver them, and it's like over like an acre. So it's huge. There's like power limitations. So it's a really interesting problem. But yeah, NASA runs all kinds of. They do everything.
So speaking of NASA, if you're curious about where you can go for more information, check out robotics.nasa.gov/edu. They list out tons of these competitions with actual rules and ideas, and then they've broken it apart into like elementary school, high school, college level competitions and activities that you can run in your classroom. It's a good site for these kinds of things. So, first, we brought up FIRST earlier. It's a good one. You and I both went the distance doing mentorship at FIRST. This is, if you're not familiar with FIRST, it is a national robotics competition, and they now have leagues for all the grades, K through 12. They have Lego Junior League. I didn't even know about Lego Junior League. That's a new one.
I think I just heard about that, but yeah.
Yeah, because I remember Lego League, and now they've introduced K through 4 doing Lego Junior League, so that's even younger crowd. There's the first Tech Challenge, which is usually smaller robots, and then the first robotics competition is for your high school level, and there's a picture of it on the left here of what one of these robots look like. They're people-sized or bigger than people, and they usually have to perform some ridiculous task. Our year, it was picking up, I think, balls bigger than the robot itself and trying to put them in baskets that were trailing behind robots, so we had to like chase down other robots. Usually FIRST has the first minute or 30 seconds of a match is autonomous mode, where it's hands off the controllers, you push a button, the operators are not allowed to touch it, the robot has to perform something autonomously, and you can get lots and lots of points if you actually complete some activities. Most robots I know, when I was there, they would just do something defensively, like spin in a circle or something like that. And then the rest of the match, which is, maybe 3 minutes or so, then you have drivers actually trying to compete and do control it with remote control.
Yeah, they always have like 2 or 3 drivers with these things because there's just so many points of articulation. So there's even the teamwork of just driving the thing.
Yeah, they give you these 2 ridiculous controllers you have to use. We had like Logitech joysticks that we had to like make talk to these robots. It wasn't easy.
That was a project in itself.
Oh yeah, just learning how to do the driving aspect. I think we threw that together in the last day because it was my first time as a mentorship, and it was like maybe the school's second year of doing this. But it was a blast. So if you're interested in running a FIRST program, most of these are run as outside of school, like extracurricular activities. I've seen some where you can take a class and they allow it as elective, but most of them are like they meet once or twice a week to build a robot. They give you the rules, and it's like January, and then you have 6 weeks to build a robot.
Yeah, usually.
I want to say it's 6 weeks, and then like a week before competition, you run like practice heats, and then there's like real competitions in your region. This is nationwide. This is all over the United States. If you're curious, check out firstinspires.org to see if your school has one, or if you want to look at creating your own club in the school. There's BEST. You and I judged for BEST Robotics, and this is also a national robotics competition. It's smaller than FIRST, and it's both middle and high school students. The thing I liked FIRST. FIRST is very impressive challenges. The thing I noticed about FIRST is, especially if it's your first year as a mentor, you're often doing the design work because you're learning it along with the kids, and you don't have much time to really help them up until the point where your school has done it for a number of years, and then you start having kids teaching kids, and you create that community. BEST, the challenges are simpler, but the focus is on the students actually performing the activities.
Yeah, BEST, the rules are that the mentors can't do any of the work. So it was very, it was really awesome to see, it's a very level playing field. So I believe BEST always tries to make it free for schools. So if you can find a BEST hub, they're definitely going to try and get you a kit. But Yeah, the idea is that everybody's on a level playing field, so you get a kit of parts. It's like the Apollo 13.
They dump it into the table just like this. And
every student has the same parts. Every student has the same kit, so it's kind of more of a level playing field in that sense. But
yeah. I noticed that it's most best hubs. Like, I didn't know what best was. I was on the East Coast.
Yeah.
But I noticed most best hubs are kind of in the middle of the United States. So it was like South Dakota, North Dakota.
It started like in the Texas
South. It's
like
big in the South.
Kansas region. I think it was like Delta or something that was the original sponsor, and so, or American Airlines was the original sponsor, and so it kind of grew from there, and it's been kind of branching out ever since. So
yeah. So that wraps up everything we've got. We've got a couple of minutes if there's any questions. No dice.
No questions.
I know.
All right. Well,
that means we covered everything, and there's nothing else that needs to be said
Done.
about robotics in the classroom.
Done. Solved robots, guys.
Solved. The issue is solved. So for 2 minutes, you want to compete? See if somebody can throw each other off the table here.
I mean,
Unless we get a question, you're just gonna watch us drive these around. Your scoop is lower than mine. Oh, that's a dance right there.
Oh man.
Oh no, I'm gonna get you. I don't know how to drive this thing.
Oh, now I gotta invert things.
Yeah.
Oh no. The dance of robots. Am I kidding?
Did it.
This is embarrassing.
It's a good thing these things are pretty indestructible.
I hope nobody from ABC is watching.
You said that you're not the driver.
Yeah.
You let somebody else drive.
Anyways.
Awesome. Well, thank you all for tuning in. I think you can post questions. If there might be a comment section on the YouTube. So after this, we'll try to keep an eye on it.
Yeah, excellent. Yeah, thanks.
Awesome. Thanks everybody.